So yeah, obviously there's an exam coming up. I hope, you know, people are feeling good about it. Now there's a variety of things that are on there, list implementations, some of the more recent stuff, problem solving, recursion. It'll be a nice, it's very convenient to take data structures during the spring, or convenient's not the right word, but it can be preferable in the fall. One of the reasons is you have the exam right before spring break, and that actually gives you an extra week to work on homework six, which is nice because you can have some extra time. So I definitely recommend getting a head start on that homework assignment. So, anyways, uh, in terms of reviewing for the exam today, there's some nice practice problems. I was going to talk about a list related problem as well as kind of applying that recursively as well, which actually was a recommended question today. Anyway, so let's um, let's start with that. And as always, if you have any questions, feel free to put in chat window. I'll keep checking back and stuff like that. And in the meantime, I'm going to open up a collab board and share my screen. All right, so I guess to start, kind of clear this up. Let's start with a very, classical and famous coding problem that has been shown multiple times on exams around this period of time for data structures on top of. It's a very famous problem. Sometimes it's talked about in lecture. Other times it's just a matter of it, just being very well known. Good way to get familiar with linked lists, recursion, stuff like that. And the idea is this topic of reversing a linked list. And it's kind of what you might think. So, and say we have like a linked list, right? And so even before that, let's just say we have a very simple linked list of three numbers, and we're given the input, which would be really a pointer to the head of the linked list. Keep in mind, we don't have access to the full structure. When we have a function that's giving us access to a linked list, it's not the entire linked list there, but rather it's a pointer that we can then use to navigate to other parts in memory of where the other nodes of that linked list are by following the pointer. So really the input here would be this, head of the linked list. But, keeping that in mind, let's say, we have three nodes in this linked list, and we really had this objective of, given the head, returning back a linked list with a pointer that's basically the reverse of this. Ideally in place in memory, meaning we're not creating new memory and just doing that all over again. We're basically taking these and moving the pointers around. So now, instead of it pointing in this particular way, where we have these three nodes, and basically it's pointing to the tail there, we can ideally put together something where the first node is kind of like this, where, three is now the head, right? And that's now pointing to two, right? And likewise, two is going to be pointing to one, kind of like that. And then lastly, now one's going to be pointing, to the indicator that we're out of bounds. So like the null pointer. And that would be the idea of, reversing a linked list. We're given this head input, a node pointer, but now the node pointer will be that three, and it will point to null in this way. And the question is, how can we kind of do this? How can we move these pointers so like two is now pointing to one, and three is pointing to two? And there's really two ways to do it. One is technically more efficient. It's the iterative approach. It's better in space-time complexity. However, it's also useful to go over the slightly worser performing solution, which is recursively, just again to get practice with recursion as well. And you could see that definitely being an exam question, as it is very often. Um, so, anyways, keeping that in mind, let's first talk about the iterative approach, mainly because the idea with the iterative approach is as we've kind of talked about, you can kind of help get a good idea of how to start doing things recursively often if you can put together a good iterative thought process, because now you at least know how to solve the problem, and now you might want to reframe it in the context of recursion, whether that be a sub problem of another sub problem, which in this case, that's kind of the right recursive way to think about this. What's this most simplest problem here, and then what's the medium-sized problem, and then what's the biggest problem? And, thinking of this in terms of sub problems will be a very good recursive approach. But to start, let's just look at this linked list here, right? We have a 1, and it's pointing to 2, and it's pointing to 3. And, we'll have, just like it had before, pointing to that, null area, just like that. And, if we want to do this iteratively, before we even write code, let's kind of imagine what we might need. Really, the key to doing this iteratively is we might need 2 pointers. And the reason we might need 2 pointers is because if we point something to another place, we might need a reference to where we were before, so we can point that arrow in the opposite way. And what I mean by that is we know in the end that if we were to kind of move these pointers around, it would kind of be something where it's not a 3, 2, and a 1 anymore. It's, perhaps it's something where we get rid of this arrow, right? And then, we point it here, and we point it here. And then, we end up pointing it here, right? Where it's kind of something like this, where in the end, the head isn't this 1 anymore, but we actually end up just treating this as a head. And, the question is, well, how can we do something like this? It kind of doesn't matter visually how we write on the whiteboard. All that matters is whatever we have in memory, when we call the next arrow, are we kind of going in the fashion where we start at 3 and then we go to 2 and we go to 1? Well, the question is, how do we reconstruct something like this? And the way you reconstruct something like this is, well, at the beginning, we definitely need a null here, right? We need a null at the beginning. And, this isn't yet connected to 1. It's just kind of out there. So we might want a pointer here, which might serve as, and let's kind of change the color here. This might serve as, the previous. And this might be useful in a sec, we'll see. Maybe this becomes our previous pointer. And then, maybe we also have something that represents the current pointer we're on. And this is at the initial state. So we're imagining this end result, which are all these green arrows, don't quite yet exist. Right now, we're still at the state where there's red. So think of this as the red drawing here is where we start. The green drawings here are where we end in terms of where the arrows are pointing. And the white arrows are going to kind of describe where we are in between, how we get from the red state to the green state, showing those sub steps with these white colors. So this is the previous pointer, and this is the current pointer. And, if we think of this very simply, if we just had a linked list of 1, right, and that 1 pointed to null to the right, well, we could, just point the next to null. That actually doesn't matter there, but we could also just make sure the next kind of points in. It's kind of misleading to say this direction, but, the idea is basically when we have a previous pointer and a current pointer, instead of the current next kind of pointing to what's over here, we could just point the next to what's over here. And then we can shift these 2 pointers kind of like a sliding window. And that's going to kind of be the key here. So keeping that in mind, right, what we can say is in this first situation, we should take what the next is currently, which is this, it's going to the right here, and we'll make sure the next kind of goes to what's to the left. And again, left and right is very misleading. These are just things in memory, but visually, when we put it on this whiteboard, we're treating these nodes as things. We'll say that they're to the right and to the left just for us to understand visually what's going on. Now that one's pointing over here, we're kind of done at this state. And what we can do is each time we can shift these pointers one to the right, right? So the previous is no longer pointing here. The previous should point to actually what the current was. So keep that in mind. After we're done, the previous should be where the current would be. Well, that's kind of a hint that we're going to have a line of code that maybe says something like previous is equal to current, perhaps, maybe something like that. So keeping in mind, how do we shift the previous here and the current here? Well, just for now, visually, let's say this is now previous. And let's say this is now current. All right, so now we're at a new state. We've basically moved the one so it's no longer pointing here, but instead pointing here, right? Another thing we're going to have to do is at this state, well, instead of putting the current dot next to 3, right, we're going to have to make the current arrow next go to the previous. All right, that's another hint. It looks like iteratively we're going to probably have to do something like current arrow next is equal to previous, right? Because if the current arrow next is going in this direction and we want it to go where previous is, it would make sense that the pointers, next attribute should point to where the previous currently is. So we have a couple lines we're thinking of right now, right? To bring the previous over here in the end, we want something like, this is probably going to be one of the last lines in each iteration, right? Maybe something like previous is equal to current, right? To shift it really in the end. Now keep in mind too, if we shift previous to where current is, well, current's now going to go to the over here to the right as well. Well, that also probably means we have to shift current to what's over here. Well, what's that? Well, that's just the next, right? So it's the next of this. So, maybe it's what current next is. So maybe we have a variable, and keep in mind, because we end up changing what next or what current is, we probably want to retain what's ahead of us before we call this line here. So maybe it's going to be something like, next, and we'll review that again, why we create a temporary variable in a sec to not overcomplicate things for now, but it's going to be maybe something like next and then current. And we'll get back to that line in terms of why it's useful. Right now, that's just storing a variable. But we do agree, at least I imagine, that, at the end of this thing where we have to shift the 2 pointers and then we want to reverse the arrows between these 2 nodes, previous has to be at current, and current's got to go on to the next, which is the current next. So previous is equal to current, and then current is equal to next. No reversing going on here yet. This is just shifting the pointers to go on to the next one. That's some pattern we keep seeing. And then another thing that we're making the connection right now is just like we're saying, well, to get current to point to previous before we shift these pointers and go on to the next one, it makes sense that current's, next should be assigned to the previous pointer, right? So instead of current next going here, current next should go to previous. So that probably means, right, in between here, we'll probably want at each iteration to have something like current arrow next is, well, equal to previous. Sorry, I don't have my iPad on me today, but I'll have it next time again. But the idea is that's kind of the reverse step in this iteration. And really, if we follow this process, next time again, right, where we kind of think of this as a loop. So, all right, we reverse this. Well, then we say previous is equal to current. Okay, that means previous is now going to be here, right? Current's equal to next. Well, we're saying next right now is this thing over here. So next is going to now go here. Then we're on to the next iteration in the linked list, right? So now here we want to say current, this should be current. Current's equal to next, right? But since current's equal to next, both next and current are at the same location. And so now when we say current arrow next is equal to previous, okay, now this is pointing here. And now we have really the reverse linked list, and now it's a while loop, so we got to, kind of figure out when do we stop. Well, it probably makes sense to go until the current has a null pointer value. So maybe the condition is going to be something like while current is not equal to null or null pointer. And then within the body of this while loop, it's really just going to be these 4 things right there, And another thing we might want to think about is I want to really reemphasize, if it's not clear already, why this first line is necessary. Like I said, we'd go back to that. So what I want you to think about is, well, what happens if we just get rid of this line here and in the end say current is equal to current arrow next? Well, in the beginning here, current means something kind of different than what current's here. And the reason is because current in this situation has a different next. So at this point, we're saying next is equal to current arrow next. which means current arrow next is something there, but here we're updating current arrow next to be the previous. So if we now refer to current arrow next down here, it would have a different meaning once it was assigned here than it would up here. For example, when we're at 1 here, right, and we want to basically get the next pointer, which in the beginning is this right here when we're currently at this 1 here, uh, to store next, we have to first say, next is equal to current arrow next. However, in the next line, when we say current arrow next is equal to previous, since this is previous, the arrow next, this next arrow, if we say this white arrow was the next arrow, uh, we actually end up updating it so the arrow next actually goes to null. And because we do this, now if we were to go down here and in theory get rid of this first line and say current is equal to current arrow next, that would end up meaning we're accidentally assigning current to here, this null value, versus in reality, we want to assign it here because we want to continue to go down that linked list. So just keep in mind, we need a temporary variable in the beginning to refer to what our original next node was later on, because when we reverse it, we actually accidentally might be going in the opposite direction. So want to make sure no questions so far. Really an important thing to keep in mind. But, with all this kind of visualized and, designed out, let's go on and, implement it. So I really think this problem iteratively and recursively is like a really good overview of kind of a lot of the core concepts from this unit. And again, a very popular exam question. But, anyways, let's, code that out. It's no different than what we described in really the core lines that we just put together. So let's say, in the end, we want to return a node pointer, right? Which is going to still be the head. And then let's say this is reverse linked list iteratively, right? We're reversing the linked list and it's going to take in a node pointer, really that head. Again, we can't take in an entire linked list. We're going to have some pointer in memory to the start of the linked list, and we can follow the pointers throughout all those memory addresses to kind of navigate and iterate through that full linked list. So that's the input there. And really what we're going to want to do is, well, if we go back to the whiteboard, right, the previous is right before this. The previous is going to be the situation where in the beginning, well, it looks like the first time we set previous to null, right? That was kind of a unique situation. And that's because the tail is always pointing in the end to null. Well, if we reverse it, 1 is now the tail, right? And that means the next of 1 should eventually be null. So in the beginning, we first said, okay, the previous and the current are going to start here. The previous is going to start at null, and one's going to, the current's going to start at the head. Okay, well, if that's the case, we should probably start this code in a way where, node pointer previous is going to be equal to, in this case, null pointer, which again is the same thing as null. And then likewise, node pointer current should probably start at the head, just like how we put it at that block 1 at the beginning. That will be equal to head. All right, that's the setup. And then we also said just earlier that there should probably be some condition to stop basically moving these pointers like a sliding window once we get to a point where current's now here, right? Because we've kind of reversed everything once we get to this 3, and this is now pointing in this direction. So the condition would be something like while current, I mean, that's perfectly valid, right? Or we could be more explicit, while current is not equal to null pointer, right? And as long as this isn't the case, then we can kind of really, we wrote out the rest of the code above here, right? We want to save as a temporary variable that next attribute. Really, what's the next before we reverse it, right? So the original next might be a better name for it. So let's call it that actually. So we'll say node pointer original next before we reverse it. Node pointer original next is equal to really the current arrow next. Secondly, right, this is where the actual reversing goes on, right? If the current's here, for example, at 2, let's say it's there at some state, and then the previous is at the one before it, that the next of the current shouldn't point to where it is before. It should now point back at the previous because we're reversing the linked list. So that's the case, right? Current arrow next is equal to previous. And then that's really the reverse step, but now we want to shift the pointers, right? We want to move the sliding window. So what was now previous should probably be current, and what's current should probably be what was the original next if we went to the right. So keeping that in mind, right? If previous was here and current was here, when we now can compare, once we, or let's think of it now here, if we reversed 1 and 2, now we're going to want to reverse 2 and 3 in a way. So if this was previous, this will now be the previous the next time around, and this will no longer be current. Current will be the one, in front of it, which was the original next. So therefore, the final two lines in this while loop will be previous is equal to, in this case, current. And then lastly, it will be current is equal to original next. Just realized above here, we used, so we're saying that next is the attribute here. So current arrow next, original next, and then current's equal to original next. So that will be good. Keep in mind, this next isn't a node. This is the next attribute, like there's the val, the next, or the previous. There's no previous because this is a singly linked list. And really, in the end, right, once we have this, we want to return the head of the pointer. Well, what's the head now? Let's go back here. In the end, right, once we go through the while loop, we're going to, at that last iteration, reverse the 3 to the 2. And remember, the previous is the one that we shift to right before it, where we point it back to. And then, current is the one that we basically are at, that we reverse it from there to the previous. Meaning, in the last iteration, current is what original next was, which is actually in the end the head. So it makes sense that current is pointing to the head of the linked list, and therefore in the end we should return current. So that'll just be return current. Check to see if there's any questions. On the exam, how can we come up with a solution faster and when approaching it to on the exam, how can we come up with a solution faster when approaching a question? What are some typical edge cases to consider? Before checking head arrow next, are we always supposed to check for head arrow next for the code to not break? Good question. So, I mean, the first question to answer, if we want to come up with a solution faster when approaching a question, I don't know if there's a very particular type of question you have in mind, or there's a particular strategy. More generally, obviously, practice problems, certainly help. So again, one of the reasons we go through these practice problems is typically once you do something like this, you start to see patterns. Recursion is a really great example. There's types of recursion problems. One we'll see in a sec is like a subproblem of a problem. That's always very helpful to keep in mind. But if there's a specific type of data structure that you're stuck, with like linked lists, it might make sense to practice a lot of linked list problems, and that can help you figure out very common types of questions, patterns, things to look out for. Maybe you'll make this connection that, oh, I need to make a temporary variable like we did before reversing it, or maybe the removal, you'll get in the habit of kind of doing those things. So it's more about kind of seeing patterns and making connections of, not only do you understand it, but kind of practicing the implementation certainly helps there. Um, Coming up with a solution faster in general in programming is just, a very, just a lot of practice, working with practice problems. And again, LeetCode is very, very helpful with that, as well as, just the general data structures homeworks. Actually, I'd even argue that maybe the practice problems are even better than data structures homework in terms of coming up with solutions fast, because those are more long-term, projects where you plan it out for the week and get that done. But to come up with something faster, you might want to work on exam size questions due to those, like, timelines of it. Now, edge cases to consider, again, that's very depending on the problem. So you want to look out for, types of errors. You want to make sure, again, very, very much depends on the type of problem or data structure that you're working with. For example, with linked lists, you might want to make sure that you're in bounds. You want to make sure that if you like reverse a linked list, that all the pointers are, referring to the right things. If you change one pointer, Are you making the assumption that this pointer is now the updated pointer, or you're not treating it as the original pointer? That might be a common bug to look out for. Again, a lot of those, common problems to look out for is, again, just things that you'll pick up when practicing. For example, just like when you practiced in the beginning with like vectors, right? One of the things you probably look out for now is if you're using an integer to index something, you'll make the connection. Oh yeah, it's very common for, I've seen, I may have accidentally gone out of bounds before in a vector and gotten, a seg fault or, something like that. And just based on failing a few times, you can kind of pick up that stuff. But, the best way to do it is work with practice problems. If there's a specific data structure or specific type of problem or, algorithm, I could definitely bring up some things to look out for there. But more generally, just, working on these problems and, failing, which you will fail. Fail in the context that when you're working on practice problems, you'll get them wrong, or you might struggle, you'll run into a bug, and picking those patterns really help when you work on very similar problems. Um, as for the next question, before checking head arrow next, are we supposed to check for head arrow next? Yes. Now that's a very good thing. Now we don't do it in actually this code. We don't do a head arrow next arrow next. We only do one arrow next. But if you had something that was in an iterative approach, right, where you're going to eventually go all the way to the tail, it's possible that head arrow next gives you null pointer. And the problem with that is you can't get the arrow next of a null pointer. So that would give you an error. Absolutely. So now if you never reach the end of your linked list and you're always gonna, you're never gonna be in a situation where you're at the tail, that wouldn't be an issue. But in that case, the edge case, right, to consider, for example, the edge cases like you're mentioning, the edge case to consider there is if you're at the tail of the node, the arrow next will be null pointer, and the arrow next of a null pointer is non-existent. So uh, to answer your question there, it's yes. So definitely another thing to really look out for if you are going to the next twice. So yeah, hopefully that helps, and yeah, feel free to ask any other questions. In the meantime, let's see if we can put this into LeetCode. I think this will be in LeetCode. I think we did a problem like this in the past. Um, let's see. Might be in another language, but let's throw it in. And that might be also useful to see the recursive one too. But let's start with this. So we'll just throw that in. Now, looks like next is the attribute we're using here. So I think this should run as is. If not, we can adjust. This is because it's called list node above here. All right, what are we getting wrong here? So we do the previous, we set it to the null pointer. We're setting the current to the head. We're going until the current is not equal to null pointer. And we update the current to be the original next. The original next is going to be equal to the current going to the next. The current next is going to go to the previous, and the previous is equal to the current. That seems to be okay. Are we missing anything in here? Ooh. There we go. We returned the wrong data type. Let's go back to the whiteboard. Once we go to the end, right? Because if you think of this iteratively, we're going until current. Remember, when we do the while loop, we're going until current arrow next, we're going until current in this loop is null, right? So if current's null, that means current will be here. And then remember, when we move current, we also move previous to the right. So at this state, it turns out current's not the head, current's actually at this null value, meaning previous actually ends up being the head once current reaches null based on just the way we move the pointers at the same time and when we stop. So the mistake there is we returned previous, or we should have returned previous. So hopefully that makes sense. And then let's talk about recursion. So this one will be a little more tricky. But let's kind of think about this in terms of a larger problem. Think of this larger problem into a smaller problem, and then think of it as a medium-sized problem, and so on. It's a little more elegant. It's less lines of code. It's slightly more inefficient. Not that recursion is always that case. That's a very common misconception. But in this case, it's not that preferable. Now, let's just again imagine three scenarios where we have a linked list. Again, we're going to keep it simple as always, with a 1 that points to a 2, and a 2 that points to a 3. We need at least 3 to kind of appreciate the recursion going on here. And then, right, it's going to signify we're at the end and know when to stop. This will point to null. And this is how we do it recursively. So before we think about, reversing an entire linked list, how would we just reverse a linked list where all we had was a pointer to null, right? What would be the reverse of just null, right? This could perhaps be our base case. Can we build off of a really small base case and then maybe build off of a larger base case and so on? Well, to reverse nothing, you get nothing. So it would make sense that perhaps, if the head, if we were given a linked list, right, where the head is just null or no pointer, we might want to just return no pointer or the head. That's one case, right? Let's say we have, maybe something not as complex as above, but maybe a little more complex than just nothing, right? Let's say it's just a linked list with one head. Let's say it's just a subproblem of this. Let's say it's just, we've kind of seen the subproblem of this, but now let's look at the subproblem of this, where I like to think of this as a linked list of like size 1, for example, where we have a 3 and we're pointing to null. Likewise here, do we really have to do anything to reverse this linked list? Well, really 3 points to null. If we reverse a linked list of size 1, it's really just itself again. I mean, visually we've kind of been describing it as, well, if it's pointing to the right, we can kind of visually think of it as pointing to the left, but that doesn't really matter too much, right? In the end, it's just giving you a 3 that its next attribute is going to give you a null value. So let's undo that. So I think we have, two base cases, right? We have the base case of nothing, which will just reverse be nothing. And then something of size 1 will again just be itself when it's reversed. And then the recursions, okay, if we can kind of keep this in mind that this subproblem is reversed and then this larger subproblem is reversed, then really it would make sense that the reverse of all of this is reversing the stuff here plus the reverse of all these subproblems. So what I mean by that, let's kind of look at, the code first and kind of go into some more detail. So this is the linked list iteration. Let's do node pointer reverse linked list recursively, right? And let's give it as input a head. And then what we'll do is we'll give it as input, these first two scenarios we talked about. So what were they again? Well, there's the case where the head is just null. Well, in that case, we should just probably return null. So if head is equal to null pointer for now, and I'll show you why in a second, let's just return head, which is the equivalent of null pointer. So that's perfectly valid to do. Return head. Right? If it's nothing, we're going to return nothing because head is equal to nothing in this scenario. Another case to consider is, well, and this is kind of like else if, because if the thing above was true, we would return there. So this is only going to happen if the thing above wasn't true. So otherwise, if head arrow next is equal to null pointer, well, this is the situation that we talked about where it was, let's go back here, where we have just a 3, right? If this is the head, this isn't null, but the arrow next is null. So this is basically talking about a linked list of size 1. So if it's a linked list of size 1, meaning the head arrow next is equal to null pointer, well, we kind of make the connection. Well, it's kind of already reversed because it's just one node that's in itself. The arrow next will still be, pointing to null. So in that case, we would return, head. Now the reason I drew it out like this is for the cleanliness of code and just writing good code. It looks like if head's equal to null pointer or head arrow next is equal to null pointer, either way you return head. So in less lines of code, we could even clean this up and say if head's equal to null pointer or head arrow next is equal to null pointer, well then let's just return head. So we've kind of reduced this from going from 3 to 8 to just 3 to 5. This cleans it up a little bit. And then now there's this idea of kind of making that connection, like we said before, that everything in front of us, if we reverse that, then we just reverse, if we can reverse the end, well, then we'll just reverse something of one node, and then we can reverse, we get the result of that, and let me kind of be more explicit. So if we reverse nothing, we get nothing. If we reverse one node, we get just that. And then reversing something of two is the reverse of what we get here with this, right? And then this here is the reverse of everything we have so far with this as well. So what that means is we want to get everything in front of us. So let's go back here. How do we get really that next node that basically includes everything ahead of us that's already been reversed based on this, subproblem that we're designing right now, right? That maybe we call it node pointer next node. And remember, this next node is kind of in that like circle that we were just drawing where that's already, been sorted at this point. So, next node is going to be equal to really the recursion, right? The reverse linked list recursion, and it's going to take in, basically the head arrow next, which we're saying everything after where we currently are is going to be, reversed already. So that would be the idea there. And then, at this point, once it's been, reversed, it would probably make sense that going to the right, so that the next of where we are here, which is the result of it being, let's kind of go back to this. So if, for example, everything in front of here is now reversed, like the 3 and the null, which again, in the end is just itself again, it would make sense to perhaps look at, again, we got here by basically saying the next node, so which is, when we're at 2, the head arrow next. So we're basically going to reverse the head arrow next, which would be reversing this based on our code, right? Next node is equal, let me kind of go back because I'm saying a lot at once. Next node is going to be equal to the head arrow next, right? We're kind of thinking this as a slightly bigger problem now. Instead of this being 3 arrow null, it's 2 to 3 to null. Well, the next of this is going to be calling the reverse on the head arrow next. Head arrow next is just this 3 and the null. Let me kind of repeat that again a little slower. So when we have, let me go back one more time. When we have a 2 that points to a 3 and points to the null, and we know that this is a much more simpler problem, it would make sense to say that the next node is basically going to be the reverse of head arrow next. Well, in this case, the next node is going to be just 3, right? That's that next node right here. And keep in mind, we call the reverse, but remember in that base case, when we just reverse this here, it's just itself. Now, keeping that in mind, if this is the head, we basically say the head arrow next is going to be equal to the node. So if we go here, this is the head, the next, and then the next is going to be what's the node here. Does this make sense? Well, we went from something that has 2 and 3 and null to something that now has 3 and 2, right? Which in this case, we haven't even looked at the 1 yet, but this is reversed now. 2 is no longer pointing to 3, or I take that back. So 2 is no longer pointing to 3. 3 is now pointing to 2. So head arrow next is equal to node because we've kind of moved this over here by going to the right here, and what was now null is this 2 value. So meaning the next line of code here will be head arrow next, and let me know if I'm going too fast. I'll check the chat in a sec. Head arrow next is equal to, in this case, node. So that would be the idea there. So from here, we want to go on to basically the next thing. Well, if we think about this, well, this is just one state where if 3 is pointing here to 2, right? And this is like a reverse linked list of a subproblem. Well, we need the tail, right? So we need to consider where's the null pointer going? Well, the null pointer should basically go here. So basically, if this is the head arrow next should basically go here. So although the head arrow next was originally pointing in this direction, the head arrow next is now going to point, again, direction is kind of misleading, but we want to point this at null. And that means at this state where we're just looking at 2 and 3 now, we have a linked list where 2 is now going to 3, right? And 3 is now going to null. So now we've basically reversed everything except 1. But keep in mind, that's okay, because the whole way we've reframed this recursion is, how do we recursively reverse null? Okay, then how do we recursively reverse 3 and null? All right, that's simpler. And then if we take the result of that and reverse that with this, now we have something there. If we take the result of all that and reverse it with this, then we're basically recursively reversing the whole linked list. So that line of pointing it to null will be something like, let's go back here. It will be, head arrow next is equal to null pointer. And then basically we're good there. So that's the case in that situation. Let's see, what is there from here? So at this point, once we've pointed it here, we want to go on to the next one. We've done the recursion. And then in the end, right, the head's going to be, we want to basically update what the head is. So that will be, we'll just check the chat first. Yeah, so we'll look like we'll show how what it looks like in the stack right when we finish the implementation. Really good idea. So let's see. So we're seeing what's pointing null pointer. Then we return the head. Then we get the next node, and then we're saying the head next is going to be equal to, it should be next node, right? And then the head arrow next is being equal to null pointer. And in the end, right, what was basically next node is going to now be the head because we're going in the reverse direction. So return next node. Make sure this works, and then we'll kind of go through the stack implementation. We put that in there. That will be, let's go in here. And then we have the head, null pointer. This will be now list node. And then that's good there. And then let's throw that in here. And I'm just making sure. So next node was the result when we reversed it, and then in the end we're returning next node. We're pointing the next none, and then the next should be going to the, this should be going to the head, right? And then let's run this through and give it a run. And it looks like we have some syntax there. Let's make sure the brackets are good. So this closes here. This closes here. We forgot the brackets there. And then this is because I think this used to be another function name. Use of undeclared identifier reverse LL recursion. Right, because this is now called reverse list up here. write different function name. All right, perfect. Let's run the submission, and then we'll go over this like a stack. And this is going to be worse than our other implementation. Actually, LeetCode's sometimes misleading. Unless it's like recognizing that it's comparing it to other recursive solutions. I'm not too sure, but let's kind of go through the code. Let's put it back in the code board and kind of imagine that stack. And again, we're going to think of this as a subproblem again. So let's go back in here. Let's put in our updated solution. And let's see. All right, so let's kind of do both. Let's think of the stack and also let's think of the drawing again. So let's say we have that linked list we were just working with, right? Let's clean this up. Let's just think of none of these subproblems. But again, really when we walk through this, each stack level is going to be the subproblem. So we have a 1, we have a 2, we have a 3, and a null. We kind of need at least 3, because remember, those first 2 are a base case. Otherwise, we just return the beginning. We need at least 3 to see some recursion going on. Go to null. And all right, let's give this a shot. So to start with, let's go here. The base case, if heads equal to null pointer or head arrow next is equal to null pointer, return head. So this is going to be the first level of the stack. Well, in our first version of the stack, we just have, again, we're kind of thinking of the stack as a situation where we have the 1, we have the 2, and we have the 3. And we're saying the head is pointing to what we think of as the head. And then let's throw in the null like we've been doing to say that this is there, because that actually is relevant here because we end up, treating that differently as time goes on and putting in new spots. So that's the first level of the stack, right? So far, so good. We're given a linked list that's structured in this way. We're going to want to reverse it, but the head's here. And then we ask, okay, keep in mind, this is just the function name. This isn't the recursion. We ask if the head's equal to null pointer or the head arrow next is equal to the null pointer, return head. Remember, we consolidated these 2 if statements into one. Was that the case? Head is not equal to null, and the next isn't. It's just going to give us a node with a value of 2 in it, right? So, in these situations, we'll want to, well, in this case, return head, but that's not true, so we won't. Then we go on to next node, which is equal to reverse list. Okay, so here's where the recursion goes on. Let's go up and build a new stack. And then in this situation, and again, really, really recommend once you write an implementation recursion and write the code to kind of justify it, build these stacks and walk through and see, does this make sense? Did I write this code correctly? And you'll be able to validate and verify in the end, in this case, that that's the situation. So now we're calling reverse list, but head is now equal to head arrow next. So actually, head should be here, right? So, all right, and then we start over. Is head, is head equal to no pointer head arrow next? No. So we'll kind of go down. We're going to call this recursively again, where it's going to be this linked list here, but head's going to now be at 3. Now, the next time we go through, it turns out head arrow next is equal to null pointer. So we do want to return head, which means, well, what happens when we return head? That's the value we get when we call reverse list here, right? Because reverse list is a function we're calling recursively. And then that last level of the stack, it's when head arrow next is equal to null pointer, which means we return head, which means we get null pointer. Meaning the result of reverse list in this case, when head arrow next is equal to null pointer, isn't null pointer, it's head, which in this case was 3. Meaning in this situation, right? Once we've had head here, and we backtrack and we get what was returned on reverse list, it's basically a pointer to this 3, which although it was here head, we're saying on line 11 that it's next node here, right? So basically, this is we'll put NN for next node. So now on this level of stack, we've popped off because we called the function, we returned, we kind of went down to that lower base case. So now we're going to do this line where we say head arrow next is equal to head. Okay, so what's that going to mean? Well, we're here. This is what head is. what's the next of head? It's what we have currently assigned as new node, right? And then we go to the next again, which right now is pointing to null, but it's not going to be that anymore. It's going to be basically what head is. Well, what's head currently? It's 2. So basically, 2 is going to go here. And then lastly, we're saying, since head is now here, right, based on that line, we're saying the head arrow next is equal to null pointer, right? This makes sense, right? We now have the null 2 to 3. We haven't yet included the 1 in here. This is no longer here. And we end up returning next node, which in this case is 2, right? Next node is pointing to 2. So now we're kind of down here where head is pointing still to 1 in this level of the stack. 2 is pointing to the next node. But keep in mind, recursively, although these variables end at runtime, right now we're not messing with temporary variables. We're messing with memory. So just like how these things above here were manipulated, these are also manipulated. There's a 3 here, and there's a 2 here, right? And then lastly, we'll have the situation where, again, on this stack, we have the head arrow next is going to be equal to the head. So to the right of 3, to the right of 2, right? Arrow next, this is going to point to 1, right? So we're going to have something where we have, in those two lines, a 3 going to a 2, going to a 1. And then lastly, we have the situation, well, 1 is now head, right? 1's now over here. The next of the head is going to be going to null pointer. Again, that's not quite exactly what we want the head to be, but that's what the variable we're using right now for it is. And then lastly, we don't want to return the head, because remember, in the end, we do want the final head, the head meaning the start of the linked list, which can take us through the whole linked list. But that's not what this head is anymore. It turns out, if you look higher up in the stack, up here, right, that's what next node was. Next node was pointing to 3, which is what we have right here, actually, at this stage. So once we kind of backtrack and we're left at the lowest stack, it ends up turning out that once we move the pointers around, that next node was pointing at 3, which in the end ends up being, although 3 was the last thing in the linked list before, it's now the first thing. And therefore, because it's the first thing, we should treat that as the head. And if we want to return what ends up being the official head after being reversed, then it would make sense to return next node, which is what we do on line 14, which gives us a result of this thing on line 30, which is a linked list with a 3 that points to a 2, which points to a 1, and that points to a null. And that's, reversing a linked list, but not iteratively anymore, recursively. In terms of big O, the runtime complexity of both of these, so runtime, let's say this is iteratively and then recursively. So the runtime iteratively will be O of n, because we want to go through each node as it gets bigger and bigger, move the pointers. Same for recursively. However, technically, like I was saying in this case, because we're building a stack indirectly recursively, for space-time, iteratively it's O of 1 because we're just creating 2 pointers, right? If you remember in the original solution down here, it was just creating a previous and a current, right? So it's those 2 pointers, regardless of how big it is, we're just creating those 2 and we're shifting them like a sliding window and moving them around. So it's constant space. However, recursively, because as it gets bigger and bigger, we're kind of building up that stack, we treat that as O of n. Meaning you could make the argument that the iterative approach for reversing a linked list here is better. So yeah, that's the idea there. I have maybe a minute or so before I hop into the next call. So are there any other questions in the meantime? I think that's a really good problem to go over to kind of recap a lot of the stuff covered on exam 2 and also based on just what was recommended to cover in general for this this review session. So yeah, feel free to let me know if you have any questions. All right. If not, I wish you the best of luck on your exam. Hopefully it goes well, and have a nice spring break as well. And best of luck on homework 6 as well. Have a nice rest of your day.